Hi there, welcome back to the formulaic approach. Now in this video we are going to be covering electrostatics or static electricity. Now I hope to do justice to everything that you need to know as far as O level is concerned. Then of course for A level students, if you don't know anything about this course, this video is also for you, but of course I have some videos I'll link in the description to help for your advanced level courses. But if you want me to actually do another recap for primarily for A level, where I'll be solving A level questions only, let me know in the comment section, and I'm going to do it as soon as possible. So in the meantime, I'd like to introduce a textbook to some of you, especially those that are writing maths in JAMB next year. Now, of course, those of you that also have problem with mathematics and physics, you see, this textbook is what I call a teach yourself physics. You see, that's why it's called Foundation Mathematics. It has, it's a very good book. I don't know how to emphasize things that much when it comes to things like this. You see, you need to just buy it to be able to tell what it can do. You see, this textbook it's not written by me, it's written by a very great mathematician that I know. Okay, so so that's just it. Buy it. Okay, it helps you a lot. You see, it's very voluminous, covers a wide variation of exam questions. waec, NECO, NAPTEP, DC, UTME, IGCSE, CBSE, Olympiad Mathematics Competition. One of the students that did Math Olympiad competition recently got one of this book for himself and gave good testimony about it. Do you understand? I even had one student who was preparing for Math Olympiad, although didn't write because of, I can't remember. Also got this textbook and, gave kudos or good report, I don't know what to say. It's a very good book. Just buy it, okay? It's a very good book, Maths, Foundation Maths. So those of you that are struggling with maths and physics, you cannot afford not to know maths and physics. If you are taking physics, you don't like maths, may you have success in Jesus' name. So that's the point. Try and get the book. Then those of you that are also taking physics, get this textbook, all inclusive physics textbook as well. Okay, get it for yourself to help you solve a lot of questions, solve questions as much as possible. So if you can buy both textbooks together, this one will help your math skill. One thing I like about the textbook is affordability and ability to read and understand by yourself. All right. So let's go to the topic already. Electrostatics. So electrostatics, the word electro means electricity and statics means stagnant, right? Not moving. So it means electrostatics is the aspect of electrophysics that studies charges at rest. So when you say charges at rest, we need to therefore understand what charges are in the first place. So we have to first talk about electric charges. So electrostatics studies charges at rest. So what are charges? Now one thing you should know is that charges are fundamental properties, or a charge is fundamental to matter. It's a fundamental property of matter. Now you should keep in mind the word property of matter. Now there are two things that are fundamental to matter. Number one is mass. Now you should know already, I'm going to emphasize this in Newton's law of gravitation, that matter cannot exist without mass. In fact, matter is the quantity of substance in matter. Mass rather is the quantity of substance in matter. So if mass is the quantity of substance in matter, that is the quantity of the thing that make up matter. So that's why matter cannot exist without mass. The same way, matter comes with charges, okay? Because charges are they're also fundamental to an atom, okay? Because atoms are the simplest forms of matter, right? An atom is the simplest form of matter. So if that's the case, then we say that a charge is fundamental to what? To an atom. Is that clear? So, but now the case is quite different with charges, because with mass and matter, we say mass is necessary for matter to exist at all. So if there is no mass, no matter. But it's not the case with charges. Charges can exist without matter. Matter can exist. Sorry, reverse is the case. Matter can exist without charge. Okay, but usually when there is a charge, then there is matter carrying it. Is that okay? So matter exists with charge. Is that okay? All right, so that's why we say it's fundamental to charges, okay? Now, Benjamin Franklin said there are two types of those charges. We have the positive and the negative charge. Actually, in his days, he actually said that the positive charge and negative charge, that charges are like fluid, okay? That the one that conducts a lot of that fluid is positive, and one that conducts less of that fluid is negative. Okay, so in other words, a charge is basically a property. Then the thing itself that carries the charges are basically electrons. So we know from the atomic models that we have three fundamental particles, which are protons, electrons, and neutrons. Protons, electrons, and neutrons. So these ones are the positive and negative ones, okay? But these are not charges, okay? This electron is, for example, is a charge carrier, so that when we say something is positively charged, it is because the thing when something is positively charged, it's because the thing has lost electrons. Okay, so loss of electrons give rise to what? A positive charge. And a gain of electron give rise to what? Negative charge. So that is what we mean by this, okay? Now, proton in itself, okay, and electron in itself, they are quantized units of charge. So they are not charges in themselves, they are quantized, that is, they have size. Okay, they are quantized units of charge such that both of them have 1.6 times 10 raised to the power minus 19 coulomb of charge. So you see, charge is quantized. That's one thing you should know. Charges are quantized. That's the fundamental nature of charge. Charges are quantized. They can be quantized. So this one will now be positive, while this one will be negative, the same amount of charge. Okay, so that's why if we have equal amount of protons and electrons in an atom, the atom is said to be electrically neutral. Electrical neutrality comes when what? Proton equals what number of neutrons. Is that clear? So, if this is the case, therefore, then we are saying that this unit of charge, the unit of charge is coulomb. The unit of charge is coulomb. And it is named after Charles Augustus Coulomb. Coulomb. This is the spelling. Now, the unit of charge is coulomb, named after Charles. So, Coulomb, August, Charles. Okay, so this guy named the unit of charge is named after him because he was not that postulated the electrostatic law, and I'm going to state that in a moment, but we are building it up. Okay, so now I said that if that's the case, then it means that 1 coulomb of charge is actually very great, because if an electron is about 1.6 times 10 to the power minus 19 coulomb, then it means that 1 coulomb of charge is about, by calculation, I think 6.25 times 10 to the power 18. You can confirm that. The way to do that is just 1 electron is equal to 1.6 times 10 to the power minus 19 coulomb. So how many electrons will be equal to 1 coulomb? Then you cross multiply, okay? You cross multiply, that will be 1 divided by this. Okay, so by the time you do that, you're going to get how many electrons can give you 1 coulomb of charge. Is that okay? So that's to tell you how great the coulomb quantity is. The coulomb as a quantity. The coulomb as a unit of electric charge is large. Okay, so that's that. Now let's talk about the first law of electrostatics. Now we're going to talk about 2 laws of electrostatics, but we're going to state the first one first here, because it's the only one that is very important for now. And that is the fact that the law of electrostatics, the first law of electrostatics, it says that like charges attract. So it says that like charges repel, like charges, they repel, while unlike charges attract. It is the same thing, it is the same law. Unlike charges, they do what? They attract. So the way I teach some people is, if they usually forget things like this, just remember that boy and girl, they usually attract, while male and male, they fight. You understand? So, okay, but either way, just remember that like charges, when it is positive and positive, or negative and negative, they will repel, they push apart. When they are positive and negative, they will attract. So that's the first one that is very important. So now, basically, let's talk about point charges. Now, what's a point charge? Now, a point charge is just a charge that exists somewhere in space. A charge alone, one charge alone. Okay, so we want to pick, let's say, a positive charge. So if we have a positive charge now, one thing that is very important about this positive charge, this point positive charge, is that Faraday said that this guy has what is called electric field around it. It means that electric field, this is the way to think of it. Electric field is just the region around a charge where the influence of that charge can be felt. So the region around the charge where I can feel the influence of that charge, that is the electric field of that charge. Do you understand? Of course, for you to feel the influence of that charge too, you too must be charged. Make sense? So basically what interacts in the field of electrostatics is actually the fields of charges. Okay? It's the fields of charges that actually interact. We'll get to that later. Now listen. So Faraday now said that we can represent the influence of this charge with using electric field lines. Now, electric field lines. So now, according to him, since there are already two types of charge, according to him, we now electric field lines for a positive charge. Let's draw that of a negative charge too. Electric field lines for a positive charge is going to go radially outward from point positive charge. Okay, and to proceed radially inward for point negative charge. For a point negative charge. So this is a positive charge sitting on its own, this is a negative charge sitting on its own. It exerts influence around itself like this. So the influence is such that anything that is coming around it is going to be feeling a force in this direction like this. So those field lines, so these lines I drew here, they are called field lines. So we're talking about electric field now. I'll still talk about electric field for calculation, okay? But I just want to expose it to you right now. Now, field lines they show us the direction of the force, okay? They show us the direction of the force that this guy influences on his environment. So, if there is a unit charge, charge here, it's going to feel a force due to this charge. Okay, it's going to feel a force. Just think of it as a magnet. Okay, when I bring one magnet close to the field, or I bring a nail, a metal, to the field of that magnet, you see that magnet is going to exert force on that guy, right? Either attraction or repulsion between a magnet that would like pole, it will repel. Do you understand? So you will notice that there is a distance beyond which that guy can no longer influence the thing that is brought close to it. So that region where it can no longer influence it is the region that is greater or wider already than its sphere of influence. That sphere of influence is going to be called its electric field, the region around it where you can feel the force due to a particular charge. Now, some of the properties of these electric field lines that I drew is that you notice they go out radially outward from positive, radially outward from positive charge, but radially inward for negative charges. Okay, so now if this is the case, then that is why this is what confirms to us why if we have a point positive charge close to a point negative charge, what you will see is that electric field lines will go from positive to that negative, from positive to that negative in this way that I'm drawing it like this, from positive to negative, from positive to negative. Is that okay? So that's the way they will proceed. Electric field lines, they will go like that, from positive to negative, from positive to negative. Okay, so electric field lines are going to go out like this now, outward, 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 outward. Never forget, outward for positive, then inward for negative. So outward will be in this direction, outward, and inward for negative. So that's why positive and negative charges, they will do what? They will attract. So that's the reason. Now keep in mind that these electric field lines, they are non-continuous, they are discontinuous. Okay, so what do I mean by discontinuous? It means that it just goes from positive, stops at negative. Goes from positive, stops at negative. It doesn't reverse. When we deal with magnetism, maybe you will understand what I mean by it is non-continuous. So here, inward, 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 inward. So that's why there's an attraction between positive and negative charges. So you see that it's making sense now, right? So radially outward from positive and radially inward for negative charge, electric field lines. Okay, and they're imaginary. Okay, so that in case you are thinking, okay, where can I find them? They are imaginary lines. Okay, so it's saying that if I have a charge around, okay, and you know that we can actually have charges in the atmosphere. Yes, we can. When we get to the concept of lightning, I'm going to explain that. So we can have charges. So if I have a charge in the atmosphere, it's exerting influence around itself. Okay, it's exerting influence around the field. It's exerting influence in the field around itself. So that's what we call electric field. So we now represent that field with lines. So the closer the lines are, number one, first, the lines never cross. The lines never cross. So where they cross, they produce a neutral point. If they ever cross, they produce what? A neutral point. Now that's why a positive charge will not attract a positive charge. In fact, when it's going like this, you see that it will look like it were going to cross here, right? So rather than cross, it will produce a neutral point here, which is a point where no force will be felt at all. This point here is called a neutral point. That's the point where zero force due to both charges will be felt. So they will repel each other. That's what you are seeing here. It's going radially outward, radially outward. They will repel each other. They will repel each other. Do you understand now? Now, like I said, the field lines never cross. Now, the closer they are together, the closer the lines, the stronger the force. The stronger the electric force. Now, electrostatic force. Now, what does that mean? It means that if I place a unit charge here, unit charge is saying 1 coulomb. If I place 1 coulomb of charge here, and I place 1 coulomb of charge here, so let's pick two positions relative to this charge here. I'm making it as big as this, okay? A point charge might just be a dot. We can represent it with a dot. I'm using this big circle here. So if I put a plus 1 coulomb positive charge here at point A, let's call this point A, and I put another one at point B here. Now, what you will notice is that the influence on point A will be stronger than the influence on point B. It is so because it dissipates with distance. The influence dissipates with distance. So the larger the distance, the lower the influence on the field. So that's another thing there. They do not cross, they're imaginary, and the closer together, the stronger. Okay? So those are the properties of electric field lines. Now, if you want more information, do well to look at the videos I will post in the description. Now, let us now go to substances that can conduct these charges. Substances that conduct charges. So substances in the universe are classified into three based on their ability to allow charges to pass through them. Okay, we have three things. We have number one, conductors. These ones are the ones that allow electricity to pass through them. Okay, and these ones, and then we have in between we have semiconductors, and then we have these ones allow electricity to pass through them well. Semiconductors, only under certain conditions conduct electricity. Then insulators never really conduct electricity except through very rigorous process such as heating them completely, like burning them up completely, for example. Then semiconductors, the energy input is not so much for it to conduct electricity, okay, but they don't readily conduct electricity, not as much as conductors. Conductors are the ones that readily conduct electricity. Are you getting it now? So now, speaking of that, then we have to now talk about how we get them to conduct electricity. That process is called charging. Now, charging is just basically making them electrically active. So we want to talk about charging, okay? So now so since we have insulators, semiconductors, and conductors, now how do we have, so we are just going to pick the insulators and the conductors. Examples of conductors, we have your iron metals. The metals, they are conductors. Then we have insulators, plastic, wood, glass, wood, all those guys, wool, those guys, they are all what? Rubber, etc. They are all what? They are all insulators. But metals are conductors. Semiconductors, there are some metals, there are some, they are, for example, silicon, for example, you should just see my video on basic, on the third day of electricity. We discussed about basic electronics, where I specifically talked about semiconductors, okay? Germanium, those guys, carbon, those guys. So, but graphite can actually conduct electricity. So in case because I said, as I said, carbon now, you might be thinking, how about graphite? Graphite is the allotropic form of carbon that can actually conduct electricity, but not diamond, okay? That's one other thing that differentiates it. So, but of course, now let's talk about charging. How do we make these guys electrically active? So for let's discuss, now there are three methods of charging, okay? The first one is charging by friction or rubbing. Charging by friction or rubbing. And this is the way we charge insulators. So because already they don't conduct electricity readily, so we have to force them by friction, okay? Then there is also charging by contact, okay? And then there is charging by induction. Induction charging is the one you are most likely to be tested on in your exam, okay? So, but let's talk about the three. Now, in charging by friction, what is happening here is that that piece of material that does not readily conduct electricity, we are going to rub it with another material. So what will happen is that both materials are going to be electrically neutral initially. So for example, if you rub a glass rod, for example, a glass rod on silk, for example, this is silk. You rub glass rod on silk. Now, initially, before the rubbing, these guys have equal number of positive and negative charge that are evenly distributed. So you can see positive, negative, balance each other. So that this guy is electrically neutral, the same way for this guy, electrically neutral. But immediately you rub them on, what will you do? By rubbing them, you will scatter the charges on the surface of this guy. You will scatter the charges. Immediately you scatter the charges, there will be what is called, after rubbing, there is what is called charge separation. Okay, after rubbing, there is charge separation. So what is charge separation? So these positive and negative charges that were aggregated together, they will now scatter abroad, such that some charges will leave to this guy, which is usually negative charges. So now what will happen is that at the end of the day, this glass rod is going to have negative charges on it. It's going to have negative charges on it. It's going to have negative charges on it. No, for glass rod, and I'm going to write you a list, okay? I'm going to write you a list for ebonite rod and 4. I think ebonite rod gets I've not performed the experiment before, okay, but I think you remember them, you should master them, okay? Just I'll list the ones you should know for you. Those are the ones that they're likely to test you on. Ebonite rod and 4. The 4 always gets the positive, so the rod gets the negative. So in glass rod, the glass rod in this case actually gets the positive, yes. The glass rod, so what will happen is that negative charges will drop on this silk, so that the glass rod will now have more positive charges than negative charges. Does not mean that all the negative charges are disappear. Only that it will have more positive than negative. Then the silk at the end of the day is going to have more negative charges than positive. Only a few positive charges will still be available. So in this case, we say that this body is already what? Charged. The way you can practicalize that is take the cover of your Bible and rub it on your hair when it's dry. Rub it very well and then cut a piece of paper. You see that paper will be attracted to that thing. Why? Because for a very short moment, momentarily, and that is the case, body here, the charging is actually momentary. Immediately after a while, the charge dissipates again. What happens is that there is redistribution of the charges again, and then they become electrically neutral again. The reason is because they are what? Insulators. I also explained this in one of my videos better, okay? Maybe I'll link that video in the description too. But I hope you already understand. That's why I'm trying to do justice to it. There is charge separation such that negative charges move on this guy. Because negative charges have moved on this guy, then the positive charges are available more on this guy than negative charge. So we say that this glass rod is now positively charged, the glass rod. Then the silk is now negatively charged. Is that okay? So in a case where you rub the following, these are the kind of questions you will see. Ebonite rod. Now when you rub ebonite rod on anything except silk, on any cloth except this thing, the ebonite rod is the one that will get the negative charge, while your hair or fur or cloth will get the positive charge. Is that okay? Will get the positive charge. Then if you rub glass rod on silk, glass rod gets the positive, the silk gets the negative. Is that okay? If you rub your plastic biro too, your plastic biro on your hair, okay, your hair always gets positive. Always remember that your hair always gets a positive charge. The way to remember that is your hair or fur is for you, so you are a positive person, okay? So your hair will get positive charge. Is that okay? All right, so that's that about charging. So that's about charging by friction. The next to consider is charging by contact. Now, how do we charge by contact? It's very simple. So this is the way, these are the two that we use in charging conductors, okay? Conductors are charged in the following way. Now, but you are most likely to be tested on induction, like I said. So this is a conductor. For example, this guy has positive charges on it, positive charges, positive charges, positive charges. Then there is a particular guy here that is not charged at all. There is a particular guy here that is not charged, that is neutral, has a neutral charge. Now, how do you get it to be charged? It's very easy. How do you get it to be charged? What you basically do is that you bring this charge and use it to touch this guy. Once it touches it, the positive charges, keep in mind that this guy has to be neutral, uncharged, okay? It has to be neutral first. So once it's neutral, then when you bring this guy, there's no charge on it at all. When you bring this guy first and you put it on it, the charges will spread over this guy. Once they spread, then this guy will now become evenly charged as this guy. So the charged body for contact charging, the charged body gains the same polarity as the charger, the charging body. The charging body gains the same polarity as the charged body. So the charger will give this guy the same polarity. That is, if it's positive here, once it touches this guy will become positively charged just by touching, okay? Just by touching. But of course, there is now another type of charging that is called charging by induction. That's number 3, charging by induction. Now, induction charging means a charge will be induced on something. In induction charging, there is no need for touch. So we want to charge this body. We usually use spheres to represent this. And keep in mind that the spheres will be sitting on an insulator. The reason is because now there's something called earthing. Now you have to understand this. I'm going to come back to this in a jiffy. Now earthing, the earth is basically, the earth cannot be overcharged and cannot be undercharged. So the earth is evenly, has abundance of positive and negative charges. So that's why if something is too charged, okay, you want to discharge the thing, just earth it, take it to the earth, and the earth will draw the charges. Exactly. So that's earthing. Is that okay? So the reason why we said you should use an insulator here is that if you use something that can conduct insulator, if you use something that can conduct electricity to this conductor here, this is a conducting sphere, okay? A conducting sphere. Now, if you use a conductor too here rather than an insulator, now it will conduct the charge to the earth. Okay, to conduct the charge to the earth. So in order to avoid that, what you do is you take your metallic sphere and with an insulator to the ground, then bring the charger, the body that you want to use to charge it, the rod you want to use in charging it. You bring it close to it. The moment you bring it close to it, what will happen? If it were a negative charge here, let me use a negative charge in this case now. My rod is negatively charged. The moment it's brought close to it, notice it's not touching it. In this case, it's going to touch. It is going to touch it so that the positive charges will distribute. But in this case here, the positive charges will distribute throughout the body. But in this case here, the positive charge, the rod doesn't have to touch it. It just comes close to it. The moment it comes close to it, something will happen. Charge separation, the same way. There's going to be charge separation here. But the charge separation that occurs here now is called polarization. Okay, polarization is induced on this guy. Now, before now, it was almost neutral, such that it has equal distribution of positive and negative. Is that okay? So, but because it's a conductor, the moment you bring this guy close to it, the positive charges, for example, you know this is negative, and remember, unlike charges attract. So what will happen is that the positive charges that were equally distributed with negative charges here before will now come close to this end. So they become positive, positive, positive here, and then the negative charges will come here. We could go to the other end. So that's charge separation. Now, if you take this guy away, keep this in mind though. If you remove this guy without doing just like this, by removing this guy, the charge will redistribute again. But yes, charges are stubborn. That's another thing. Yes, charges are stubborn. The day I went to their village, I saw the way they were behaving. I know they are stubborn charges. All right, but that was just a joke, okay? That was just a joke in case you are thinking that all right, let's go. So positive charges and negative charges, like I said, they will distribute, they will separate. Now, in order not to cause this charge now to redistribute, to come back together, okay, to discharge, that's discharging, what you will do is that you will now bring a conductor that will cause, for example, you can use your hand. Now, if you use your hand, your leg has to be connected to the earth. Okay, if you have ever seen some electricians or some sound engineers, they might be touching the knob of the head of a conductor, and they will remove their slippers and touch the ground with their feet. What they are doing is they are trying to earth it. The moment they earth it, it means that the charge is being conducted to the earth. Is that okay? All right. So my point is that with this guy here, when you put your hand, for example, and your leg is connected to the ground, your leg is put on the ground, you're barefoot, not inside shoe, because the shoe might insulate it. So if your barefoot is on the ground, then this charge will be conducted by your hand to the earth. Or if you don't want to do that, maybe you're so scared, you put a wire, and then when you connect the wire, you connect it, the wire will touch the earth. Usually in physics, we represent this earthing with this sign, So now, but keep this in mind though. After using this wire to conduct it, the first thing to remove is not this guy. If you remove this guy while this thing is being conducted, it will still redistribute. So what you do is, after conducting all these negative charges out, okay, what will happen is that you now remove the earth while this charger is still close to the sphere. After earthing has been done and you have removed the earthing wire, you still leave this guy close to it so that only positive charges are now here. Then you now remove this guy gently. After removing it, then this guy is now positively charged. Keep in mind, contact charging, same polarity. Induction charging, opposite polarity is gained. Do you notice? All right. Now, let's go to, we have talked about charging. Let's now talk about some devices, okay? Now, in those days, the device that was used to measure electric charge were electrophorus and electroscope. Okay, electrophorus and electroscope. But we'll be dealing with electroscope in this case. So let's talk about the electroscope. Now, especially the gold leaf electroscope. Okay, in those days, the people that electroscope, the people that performed magic, okay, in those days, they called it magic, and they called them electrician. So, today, if you talk of electrician, there are people that work on these things, right? But in those days, electricians were those that used electricity for magic. And gold leaf was one of what they used. So what they would do is that they would rub their hand very much so that it is friction. So during this Harmattan season, for example, when they rub their hand so much, then that hand becomes charged. So by the time then they will now put gold leaves leaves on the floor, those gold leaves will now be attracted to their hand. Then people will begin to see that, oh, and like they're doing magic. Okay, so that was, one of what they used gold leaf for, but not the electroscope, of course. The gold leaf electroscope is a device used to detect charge. It is used to detect charge. Electrophores can measure the charge. Now, to detect charge, if a body is charged or not. And of course, also detect the type of charge. It can detect the type of charge. It primarily consists of a metallic knob that is connected inward and a gold leaf hanging out from it. Then there is a conductor around it as well, a metallic brass surrounding it. Of course, the internal is also metallic. Okay, so the primary things that you should know is that there is going to be an insulator between this guy and this plate here. There's an insulator here, okay? There's an insulator here. Okay, so the moment this guy is charged, okay, oh no, first, how do you get to charge this guy? You can charge this guy by contact or induction, okay? You charge it by induction or contact. And it is by the deflection of this leaf that you will know if it is charged or not, okay? So for example, if you charge by contact and it gets a negative charge, for example, what you see that this thing will deflect away from this part to deflect in this direction, all right? But how do you know is it to detect charge? So for example, if our gold leaf was already negatively charged, if you bring a body that is positively charged to it, this is opposite polarity. Now, this body, because it is oppositely, the polarity is opposite to the charge of the electroscope. By the time you bring it close to the electroscope, it doesn't even need to touch it. By the time you bring it close to the electroscope, this leaf will converge. It will close up because the polarity of the body is opposite to the polarity of the electroscope. But if you were to bring a rod that was negatively charged, which has the same polarity as that of the gold leaf will do what? It will diverge. It will diverge wider. So once it diverges wider, it means it has the same polarity. Is that okay? So that's how we use it to detect a charge. So that's that on electroscope. Now let's talk about we talked about charging, we talked about electroscope. Now let's talk about the concept of charge distribution. Now, with charge distribution, one thing that you have to know about is that when a body, for example, a body, the shape of a body, the shape or orientation of a body, determines the distribution of charge, okay, in it. So, for example, for a hollow metal sphere like that, you don't expect, no, not like you don't expect, a hollow conductor, a hollow spherical conductor. It's not you don't expect. It is actually found, rather, that the charges are not concentrated in the center. The charges are not concentrated in the center. Rather, the charges are on the edges. Is that okay? The charges will be concentrated on the edges. Okay, so that's how charge distribution is. And then if there is a steep or pointed edge, is this the spelling of steep? The tip, I don't know. Pointed edge, vertex. Okay, if there's a vertex or a pointed edge, charges are usually concentrated there. So, for example, if I say which of this part of this object will have the highest charge, will have the most charge, it is this point here that is pointed. So charges will concentrate here, and they will now distribute themselves around here. And in fact, a little more here than here. Then, of course, like this, but will be more at this tip edge or pointed edge rather. So that is for charge distribution. Now let's now talk about lightning and lightning conductor. Now what is lightning? Lightning is the flash that you see when charges build up in the cloud. Okay? When charge is built up in the cloud, I'm trying to rush this so that we'll go to calculations already. Now, when lightning is formed, when you see in this atmosphere now, in this lower atmosphere, there are charges around too. There are charges around. So that's how we are able to study the cause of electricity. Lightning is also electricity, basically. It's actually spark. It's actually spark that is showing that you see as lightning. So the thunder is the sound, the lightning is that flash. So what happens is that charge are going to build up from the ground, okay? Not just on the ground, there are also clouds, lightning clouds, they build up charges, okay? Now, those charged clouds, one is going to build up positive charge, some will build up negative charges. What happens is that suddenly sometimes the negative charge are the ones that usually jump. They can just jump, but both charges can jump, okay? So when there is a jump in the clouds, okay, that's when you see spark, it produces a spark, okay, when the clouds jump and they interact with their charges. What they do is actually they are discharging. When those two clouds have two opposite polarity, when they interact, they discharge, okay? So if it happens with the ground, it's such that, for example, this rod I'm looking at outside, there's a rod in my house, the rods in your metallic socks in your house, charges will build up on their body and build up to the tip top, okay? When it builds up to the tip top, then charged clouds that are closer to that area of your house, they're also going to build up. So those charged clouds, as they build up, they might build up negative charge, and from the ground, positive charge has been built up to the tip of your house. Just follow me. What will happen is that when those two charges interact and there's a jump in those charges, then you see a spark. Do you understand? That lightning, that light that you see there is the charge that is being conducted back to the ground. Is that clear? So now, why do people get electrocuted in such a house? Is that if, for example, there's something called lightning conductor. That's what we use to control lightning conductor. If you have checked the roof of your house, you see what looks like this, okay? You see what looks like this. Just pardon my house, okay? It's something like this. This is the way a house is now, you know. So now you now see something like this, like a cross sign or something here. That's just one pole, okay? That pole is a lightning conductor. You will usually see a wire that passes around it and it is connected to the ground. So it is earthed. That wire is earthed, okay? Earthed. Now, why is it earthed? It is such that when lightning charges actually build up, you remember I said they always build up in the tip top, right? Topmost part. So if charges are building up on this roof, they will come here, they will aggregate at the tip top. So because of that, this wire is connected so that when the upper clouds build up a different and opposite polarity, and this one has been building up, positive charges have been building up on this thing, has building up from any part of this body, and they get to aggregate here. What will happen is that there might be, in a spark cloud here, there might be a jump in the in the charge. When they jump, then you see if the lightning conductor is not there, there will be electric spark, and this house might even burn sometimes, depending on the size of the clouds that interfere. So by the time the spark cloud does the thing, this guy is going to conduct the electricity back to the ground, okay? And so the ground is able to swallow it up. So there was one day I saw the ground, it opened up its mouth and swallowed the charge. I saw it, but I didn't know that I saw it. It's only you I'm telling, or don't tell another person, okay? Between me and you, okay? Because these things, they happen. Do you understand now? But anyway, let's go back to class. Now, like I said, since there is also charge distribution, if you have seen trucks before, you see trucks that carry fuel, for example, or that carry heavy materials, they usually put a chain behind them, right? They usually put a chain behind them, okay? So that chain is for a reason, yes. Now, the reason is during hot weather, for example, or very dry weather condition, charges might build up on this thing due to friction. So that this thing will not, if it were carrying something inflammable, so that it will not explode, what will happen is that they will put a chain here. That chain is for it to come to this edge. The charges will be usually concentrated at the edge, like we said. Is it becoming more sensible to you now? It's going to build up at the edges. So because of that, they will be conducted to the earth. Once it's connected to the earth, they will be conducted to the earth immediately. They will be conducted to the earth, such that this thing will not, there will be no spark, and this thing will not what? explode. All right. So now let's go into electrostatics properly. Let me pause it and clean the board. Now, this time we're going to start calculations. So, if you have not gotten this book, like I'm saying, or like I said, make sure to buy it. Foundation Mathematics. Foundation Mathematics is going to help you a lot. May God bless you as you buy it, okay? Because I'm tired of students complaining that calculations are too much in physics. Well, I don't know what you want to do in physics if you don't do calculation, you know? So, God will help you. Let's go. Now, let's go to Coulomb's force, okay? The electrostatic force. Let's start with that. The electrostatic force. So, Coulomb in 1880, where did I usually forget is it? Charles Augustus Coulomb found out that there is a force of attraction or repulsion between charges, okay? So according to Benjamin Franklin, those two attract the unlike ones and the like ones repel. So Coulomb was able to quantify the magnitude of the charge, the magnitude of the force between them, whether it is attractive or repulsive. He was able to calculate it, and he found that the force of attraction or repulsion between two charges is directly proportional to the product of the charges. Let's say the charges are big Q and small q, big Q and small q over, and the same force is inversely proportional to the square of the distance between the two charges. So what this law means, if you bring it together, it becomes that F is actually equal to KQ over R squared. This is what the law is saying. That is, the force is directly proportional to the product of the charges, but it's inversely proportional to the square of the distance between them. That's why it's called the inverse square law. It's also an inverse square law. Okay? Now, one of the questions that you're likely to be asked is that if I increase the value of this guy by a factor of 2, if I increase the distance between two charges by a factor of 2, what does this literally mean mathematically, in fact? When you see that something is directly proportional to the other thing, it means that if the size, if magnitude of the charges increase, if magnitude of Q1 or if big Q or small q increase, comma, what will happen to the force? The force will increase. The force will increase. The force is influenced positively. The force increases. The force increases. But if the distance, if R increases, this is what it tells you, that the force will reduce greatly. It reduces greatly. That is, now, for example, if the distance R increases by a factor of 2, by how much will this guy reduce? So if the initial force was actually KQQ over R squared, now and I increase R to I double R. If I double R, then this is my F1, my F2 will become KQQ over, Q did not change, K did not change, K is a constant. I'm going to discuss K soon. I want you to know the relationship between them. Now R has become 2R. Maybe it's R1, so it's now 2R1 squared. So F2 will become KQQ over 4R1 squared. By the time you square 2 to be 4R squared. Now, what has happened to F2? F2 value is now, what is F1? F1 is KQQ over R1. So that will be KQQ over R1 squared, right? So if we isolate this, it means that F2 has become F1, because it's F1 here. Everything here is F1 over 4. What do you notice? That is, if the value of 2, if the distance increases by a factor of 2, the F will increase by a factor of 4. Always the square of how much factor that increases this guy. So what that means is that if the force increases by a factor, if the distance increases by a factor of 4, the distance increases by a factor of 4, the force will increase by a factor of what? Of 16. we reduce, sorry, by a factor of 16. What does that mean? It means that if F1, it means that if R increased by a factor of 4, F2 will be equal to F1 over 16. I hope you understand me now. So that is how to get an answer without even solving question. Now let's quickly talk about the constant. Now this constant of proportionality actually has it's force, so it's going to have a unit of Newton, right? This constant has a value of 9 times 10 to the power 9 Newton meters squared per coulomb squared. Now there is a point with this thing. Coulomb actually calculated this constant by using 1 over 4 pi epsilon naught. Okay, epsilon naught is called permittivity of free space. Permittivity of free space. I'm quickly going to talk about permittivity now. Now, permittivity of free space is a constant that has the value 8.8 times 10 raised to the power minus 12. Okay, the unit will be, I don't know, just do that. Just turn this formula. This formula can therefore turn to F. This formula can become F is now equal to 1 over 4, because K is 1 over 4. That will be QQ over 4 pi epsilon naught R squared. I have done a lot of video on this thing before, so make sure you see those videos. I will link in the description. So, but this is the point now. Let me quickly talk about permittivity of free space. There's something called permittivity. Okay, permittivity is just how much a particular medium allows for conduction. Okay, allows for interaction of charges. That's what permittivity is. So there's something called relative permittivity. Relative permittivity. Relative permittivity is just epsilon sub r, and it is given by the permittivity of a particular medium over permittivity of free space. Okay, relative permittivity is what? Permittivity of a particular medium over permittivity of free space. Such that, now, why am I giving this formula? It is such that if you are giving the permittivity of medium, this formula, if you are giving that, what is the force of attraction between so and so in a given medium, and you are giving the permittivity of the medium, F will become QQ over 4 pi epsilon medium over R squared. Is that clear? Now, what that tells you is that, what if I'm not giving the permittivity of that medium, and I'm giving relative permittivity, and I've given you that this one is a constant? Then you say that since from here, from this, so let's call this equation 1, let's call this equation 2, let's call this equation 3. So from equation 3 now, I can say that permittivity of a medium is equal to relative permittivity times permittivity of free space. Is that clear? So that my formula F will become the force of attraction or repulsion becomes QQ over 4 pi epsilon R epsilon naught R squared. Is that clear now? So that's permittivity of medium. So these are just so this is equation 4. These are just the different things that can happen to that equation. All right, so let's solve a question, for example, that says find the force of attraction between a proton and an electron separated by a distance of 5 centimeters. So for example, they are separated by a distance of 5 centimeters. Let me pick my calculator because we'll need it here now. Let's just get the like this. Calculator is not coming now. I'll get a calculator again. So find the force of attraction. First, how do I know that it will be attraction? Your question might not tell you the attraction. All you have to know is the charge that they carry. Proton carries positive, electron carries negative, so I know it will be attraction, opposite charges. So how do I do this? What am I looking for? I'm looking for the force. What is charge 1? Q1 is proton, and the size of the charge of proton is what? 1.6 times 10 to the power minus 19 coulomb. While the second charge is electron, so Q sub P and Q sub E will be what? This one will be, sorry, proton is positive, electron is negative, minus 1.6 times 10 to the power minus 19. But the sweet thing about this is that right now, because we are not doing vectorial analysis, this guy, the charge of this guy does not really matter yet. Is that okay? Does not affect the magnitude. Then what's the distance between them? R is 5 centimeters. Always converts to meters. To meters it becomes 0.05 meters. So our formula F therefore becomes K, which is given by this, given as this for O level. You can directly use that. It becomes 9 times. Recall that K is F is KQQ over R squared. That becomes K, which is 9 times 10 to the power 9 times Q, which is 1.9, 1.6 times 10 to the power minus 19 times second Q, 1.6 times 10 to the power minus 19. Notice that I just eyeballed the negative charge because it doesn't affect it, right? Then 0.05 all squared. Let me teach you how to operate with this one. So to do this, simply square this 5. When you square the 5, your guy reverts to 1.6 times 9. Let me get a calculator. 16 times 9, right? 160 minus 16. All right. So like I said, 1.6 times 1.6 is equal to 2.56 times 9 is equal to 23. So you see that I'm solving it. I just multiply this by this by this to give me 23.04. Then times 10 raised to the power. You see why we need maths now? 9 times this will give me minus 19, then minus 19. Of course, you should already know this. So if you don't know it, buy this book I'm talking to you about. Indices in that textbook is explicated to the basic level, from basic to advanced. Okay? So 5, if we square 5, that's 25. Okay, I wanted to show you this. 25, I'll just square 5, 25 times 10 raised to the power. Here, I'll just put raised to the power minus 4. Is that clear? That's how to work with that one. Very simple. So that becomes 23.04 times 10 raised to the power. Here, 9 minus 19 minus 19 minus 38. 9 minus 38, that's 29. So minus 29 over 25 times 10 to the power minus 4. So 23.05 divided by, I'm just going to solve this, divided by 25. Because it will be faster. So that will be 0.92 times 10 raised to the power minus 19 minus, now division here means minus, then minus this 4. Okay? So this becomes, let's bring it up here. This becomes, now let's bring it here. This becomes, this one alone becomes 9.2 in standard form times 10 to the power minus 1, right? Then times 10 raised to the power minus 19, sorry, 29. Minus 29 minus, that's plus. Minus 29 plus 4 over what? Minus 29 minus 4, that'll be plus. That'll be minus 25, right? So minus 25. So minus this, minus 26, right? Minus 26. So our answer becomes 9.2 times 10 raised to the power minus 26 Newton. So that will be the value of the force of attraction. In this case, like we said, it will be attraction. So now let's go on to the next thing. So I'm assuming you know how to solve for forces now. I'll do, okay, let me first quickly just go over this so that maybe I'll take a question or two on vector of this. Now, the next thing we have to talk about is electric field. So you know, we have already talked about the fact that electric field is the region in space around a particular charge where the force due to that charge is felt, right? So you have to understand in this case what is called source charge and the test charge. Now listen, the source, if I am talking about this positive charge will be called my source charge. If I'm using this charge to test the strength of this field, this will be my test charge. Is that clear? Now listen carefully. The formula that you usually see that confuses students is this, that electric field is the force per unit of charge. Now listen, this one here is the force per unit of a test charge. placed around this positive charge. Is that clear? The second formula, let's simplify this formula. This is equation 5. Let's simplify this formula. E field therefore becomes F, which is KQQ over R squared, right? This is already F times 1 over Q. So F times 1 over Q. Is that clear? So Q will take care of Q, then E now becomes KQ over R squared. Now this Q, keep in mind that this Q I said is what is the test charge placed in the field of that guy. This Q here is the source charge producing the field itself. Is that clear now? So this one is the electric field due to the source charge. You just say KQ over R squared. So what this over R squared means is that the electric field at a point away from that charge. So if I say, what is the magnitude of the electric field at a point that is 2 centimeters away from a charge? Let's do that. See, find the intensity. This is the electric field. The electric field is the region, okay? The vector itself, the magnitude itself is called the intensity. That is the strength, electric field intensity or electric field strength. Okay, that's what it's called, E field. All right. So find the intensity at a point that is 3 centimeters away from a 9 coulomb or 9 times 10 raised to the power minus 5 coulomb charge. So now this is telling you that from this charge, if you are 3 centimeters away from this charge, what is the amount of force you will be feeling if you are a 1 coulomb charge? Is that okay now? All right. So the formula will be E will be equal to E will be equal to KQ over R squared. So this one is equation 5 now. This is equation 6 rather. So E therefore becomes K. What is K? 9 times 10 raised to the power 9. Then times Q. What is Q here? Is the source charge that is producing that electric field, raised to the power minus 5, all over R squared. What is R squared here? Our distance is R is 0.03, right? So by the time you do R squared, it becomes 9 times 10 raised to the power minus 4. I'll just square this guy and put this guy raised to the power minus 4. Is that clear? Now, how did I get that? For those of you that might be thinking, the more reason why you need to buy the book I asked you to buy. If you have this is the same as 3 times 10 raised to the power minus 2, right? If I square this, 3 squared 9 times square this 10 raised to the power minus 4. This is the same now. All right. Just in case you are confused. Power minus 4. 9 takes care of 9, isn't it? Isn't it? So from here we can say that E therefore becomes 9 times 10 raised to the power 9 plus minus. Addition of base means subtraction of power. Multiplication of base means subtraction of addition of power. Multiplication of base means addition of power. So plus minus 5 means minus 5. Division of base means subtraction of power. That will be minus 4. This 4 here. So this becomes 9 times 10 raised to the power 9 minus 5 plus 4. Is this clear now? So this becomes 9 plus 5, 13. 9 plus 4, 13 minus 5. That is 8. So our answer is 9 times 10 raised to the power 8. But if I now say what is the intensity on a 5 times 10 raised to the power what is the intensity on a 5 times 10 raised to the power minus whatever guy? The unit is Newton per coulomb. I did not mention that. So this will be Newton per coulomb. The other one is Newton. Okay, I put that. So if I say the intensity at a point is this, what will be the intensity that will be, what will be the force? Find the force. Find the force on a 2 times 10 raised to the power minus 3 coulomb placed at that point. The other way this could be written is 2 times 10 raised to the power 10 millicoulomb. I've already addressed this before. 2 millicoulomb, 2 millicoulomb. So if you don't know the meaning of all these subscript, all these what's it called now, symbols. See my video on quantities and units. I think I mentioned a lot of this. Okay, so that one milli means times 10 power minus 3. So if you are told to find the force there, you already know the intensity. So you use this. This is now the test charge. Is that okay? So force will now be equal to what? EQ. Let's call this equation 7. Is that clear? So make sure you are taking note of all the equations I'm using to solve now. So F now becomes E, which is the 9 by 10 to the 8 times Q, which is that source charge, test charge. Okay, 2 times this, 18 times 10 to the power 8 plus minus 3. So that's 1.8 times 10 to the power. When I put 1 point here, it will become 1, right? 1. So 1 plus 8 minus this 5, that's plus 5, that's 6. 1.8 times 10 to the power 6. Now, Newton, that will be the unit of the force, since it's force we're looking for. Is this clear now? So this has to do with electric field intensity. For the vectorial form, I will link a video in the description. I don't want this video to be too long. I'm just showing you the formulas and how to apply them. Now let me clean the board and let's go to electric potential. That's the next thing. Now, let us talk about electric potential. What is this? Is it glowing blurry? All right, let's now talk about electrostatic potential. Is it clear? All right. The video was becoming blurry. Electrostatic potential. Now, please, you see, if you have not been listening since, which I doubt, make sure you listen to this part. Because, see, if you understand this part, you understand voltage in electricity. If you understand this thing, I want to teach you now. So things, naturally, they want to flow from, look at this thing. Which of this is likely to occur? Is it that, let's call this ball A, let's call another ball here, ball B. Is it for this ball B to go up that is likely to occur without anybody doing anything? Or ball B to come down here? Which one is likely to occur? Of course, you would agree with me that if ball B comes up, you know it's witchcraft. Do you understand? It's witchcraft. So there is more likelihood of ball A to roll down than for ball B to go up. Do you understand? So naturally things want to go from a higher energy state to a lower energy state. So I'm going to use this thing to explain first. Now there's something called gravitational potential. Okay, and there's gravitational potential energy. See, the gravitational potential energy is what we call, that we use the formula mgh to calculate. You see, gravitational potential is the work done in bringing a point mass. This is not a point mass, a unit mass, not a point mass. A unit mass from one point. For example, usually our reference point is the 0 point here, the ground has 0 energy points. From this point to this point, that's the gravitational potential of this point. That is, the gravitational potential is the work done per unit of mass brought to this point. But the gravitational potential energy that this body has at this point is the work done on this body. Do you understand? Or the work done by this body coming this height. Do you understand? That's why we have this guy here, mgh. Recall, work done, force times distance. Is that clear now? So if that is the case, now listen, things naturally want to move from a high energy state to a lower energy state. Good. Keep that in mind first, keep that in mind. So if you understand now let me explain electrostatic potential. Electrostatic potential is denoted by V first. Put that in mind. It is the work done per unit of charge brought from, for example, infinity to a point. I have used the concept of infinity and I generated the formula, okay? But I don't want to do that in this video because this is like a crash course. So it's the work done per unit of is the work done in bringing a unit positive charge from infinity to a point. So work done per unit of charge brought from infinity to a point. Is that okay? While the electrostatic potential energy is actually the work done itself, which is the charge brought times the electric potential of the point in which it is brought to. So that charge, for example, we have an energy equal to the charge times the potential energy at that point, times the electric potential at that point. If I bring charge from here to here, for example, the work done, if I bring a charge from a point A to a point B, now I'm going to explain something here too, okay? If I bring charge from a point A to a point B, the electrostatic potential energy will be the Q times the voltage, the potential at point A minus the potential at point B, depending on which one has a higher potential or which one has a lower potential. Is it clear? But now, keep in mind, for this electrostatic potential energy, there is something that happens. If this point A has a positive charge, and point B has a positive charge, if I bring a positive charge in this direction of B, the electric potential, the energy of this charge will increase. Why will the energy increase? The energy will increase because it is flowing against electric potential at this point. The direction of electric potential, that's electric potential. It is coming in this direction that is increasing its energy. Why? Because the natural direction that this field will direct this guy is away from this guy. So because of that, it is flowing against that field, then the potential energy will increase. Think of it as, since the law states that positive charges will repel, two positive charges will repel, then this guy is now forcing itself. As it's trying to repel, it is forcing itself. So because of that, it will require a lot of energy. So when it is coming towards like charge, the EPE will increase. But if it is moving away from like charge, the EPE will do what? Reduce. Is it clear? So if point A were to come to point B, EPE will increase. If point A were to come to a particular point C here, EPE would what? Decrease. Why? Because this is the natural point that it wants to go to. The same for, what if it were a negative charge that wants to come to a point B here from a point A? Now if it were to come here, if this negative charge were to come here, the EPE of this charge will increase. The electrostatic potential energy of the charge will increase. And if it were to come to a point C, because the natural tendency is that it's being attracted towards here. But if it wants to come to point C, the EP will increase. Is that clear? So what does it tell you? Since you already understand this concept now, EP will increase in this direction for a negative, or to reduce in this direction for a positive, for a negative, because in this direction is being pulled towards. But if it now goes against it, it will need a lot of energy. Is that clear? But now, so since you understand that, let me now say the right terms now, the correct terms, that this point here, point B, is a low potential for this negative charge. Is a low potential point for this negative charge. While this point here is a high potential point for this charge. This point here, for this charge, this point here is at a high potential than point A for this negative charge. While point B is at a low potential for this negative charge. Why? Because to find it easy to move here. That's just the meaning. Do you understand? For this guy too, point B will be a high potential for this charge, and point C will be a low potential point for this guy. Do you understand? So electrostatic potential here will be low for this charge, and electrostatic potential, you will soon see, okay, from formula you can already tell, that is determinable, it depends on the point, on the test charge that is being brought there. Exactly. So now let's, we'll call this equation 8, so I'll call this equation 9. Now there's something I want to talk about now with batteries. So these are two poles of your batteries. They have a positive and a negative end. Now conventional current, if you connect batteries like this, hook it up to something, maybe to a light bulb for example, what will happen? Conventional current will flow in which direction? Positive to negative, right? If I put this in circuit, you know this will mean this, okay? But I want to show you what is happening inside the battery. Now, what will happen here? Electric I just want you to understand. Maybe tomorrow I will leave video on electrodynamics. See, current flows from positive to negative, right? But actually, electrons are the ones moving. Electrons are the ones moving from here to here. So why are electrons moving from here to here? So electron flows in direction that is opposite to conventional current. Note that. Then for those that don't understand, see my other videos that I will link in the description. It is because current is described in terms of positive charge. So we know that positive charges are moving from here to here. And that makes sense because this point here is a high potential point for a positive charge. This point is already positive, so it's going to be moving, positive charge will be moving to a low potential point for them. This point is low potential for them because they don't have, it doesn't give them stress to move to this point because they are already being drawn to this point. Exactly. So that's why conventional current flows in this direction. But if you define it in terms of electron, you will see electrons move from negative to positive. Why? Electrons are negative charge carriers. They are already here, which is a point that is at a high potential for them. The moment you hook it up to a point of low potential, they start moving to a point of low potential for them. Is it now clear? Good. Now let's go to let's now do my some fine maths with this guy. So V therefore becomes work done per unit of charge. Now remember that work done is actually force times distance, right? If that be the case, then we are saying that what can we do here? There are many things we can begin to tweak here. There are many things from here. We can first tweak this to become work done being force times R. So this will be equation 10. We can also say that work done, since it's force times charge times distance, and force is KQQ over R squared. So times R. If you take care of one R, then work done becomes what? KQQ over R, equation 11. Another thing we can tweak here is that we have gotten this for work done. Then we can bring that in, that V is therefore KQQ over R. This one is from equation, this is from equation, which equation is this now? 8. From equation 8 now. We can say that work done over Q, so divided by, that's times 1 over Q, right? Q takes care of Q, and we have that V equal to KQ over R. Is that clear? So these are all the equations that you need for electric potential and electric potential energy. Is the energy at that point? Just see my videos, you understand better. I want to rush on. Now the next thing you should know is what is called electron volt. Okay? Electron volt. Now, electron volt is the energy gained, okay? Is the energy gained by an electron. Energy gained by an electron. When it moves through a potential, electrostatic potential, a potential difference. This is what you call potential difference here. Is that okay? The potential difference of 1 volt. Is that clear? So it will be the energy of that electron. Yes or no? So this is the energy. This is the energy, okay? The energy of that electron. And what is energy? Energy is going to be what? Energy, which is work done, right? You know they are interconvertible. So that is equal to QV, right? Energy of a moving electron, what? Kinetic energy. Does that make sense? The kinetic energy of an electron what? Equal to QV. That means that what is the formula for kinetic energy? Half mv squared is equal to, keep in mind that this is small letter v, Q capital V. This is voltage. Don't forget that. Electrostatic potential is what? Primarily what? Voltage. So it has the following unit. I'm sorry I didn't mention that. What unit of work done here? The unit will be what? Joules. So here will be unit will be joules. But the unit of this one is either you say voltage, or in terms of what you have here to be joules per coulomb. Voltage, unit is voltage or joules per coulomb. Now, what does that tell you? It tells you that, first it was named after Alessandro Volta, more of that in advanced A level. So, from here, you can begin to do all manner of things. You cannot be doing anyhow. Just so, for example, don't do anyhow, okay? Don't do anyhow. Because I don't know what we'll do next here. Okay, let's call this equation, I've done equation 12, let's do equation 13 here. We can also do something here, see, this is half mv squared equal to q times, what is v? V is w over q, or v can also be, V can also be, let's do, let me show you something here. There's probably another equation we didn't derive it. You know that this guy is also EQ, right? W is also what? EQ. I mean, from the ozone equation we derived that F is equal to, that E is equal to F over Q, right? Force per unit charge. So F will be equal to what? EQ. If that's the case, if we substitute into this equation, W will become EQ times R. That is W. So that the voltage therefore becomes EQ over R, EQR all over Q. So that Q will cancel Q, then V becomes ER. Please, I did not give you this formula. It's very wrong of me. This formula is very important as well. Very important. This gives you, this is equation 14 now. Now let's call it equation 13 and call that 14. So this gives you that voltage, the other unit of voltage is what? Newton per coulomb per distance. Newton meter, so that will be Newton meter per coulomb. Is that clear? So this will be equation 14 now. So from this equation here, V is ER, right? So I can say ER. I'm looking for something closer to this, so that mv squared is equal to QER 2 times 2 cross multiply 2QER. So from here we can say that the velocity of the electron will be equal to 2QER over m, the square root of both sides, right? So that V will be the square root of 2QER over m. Everything all together. This one is equation 15. You can also have that. What we wanted to take the, what else can we take from here? You know, R is distance, right? And what is formula for, okay, what if we are trying to find the acceleration of the electron? Now remember that acceleration is velocity over time, right? Acceleration is velocity over time. Now, and time is velocity times distance, right? Because this velocity is distance over time. You know that velocity is distance r in this case over time, right? So that distance r or t will equal to r over velocity, right? So if that's the case, I can say that acceleration therefore equal to v over r over v over r over v. V goes up, A becomes V squared over R, right? Good. So if that's the case, then from here, look at what I'm doing, or just look at what I'm doing. You know, we've gotten that from here. Let me just go back to this place. That mv squared is 2QER. So V squared from here, let's call this V squared. You will recall that I'm just trying to bring in stuffs, okay? Just stick with me. A equal to V squared over R. So V squared here will be equal to AR. So if that is the case, then V squared here will be equal to MAR. Is that clear now? Is equal to 2QER. R cancels R. From this case, you can say that acceleration is equal to 2QE over M. Is that clear? So that will be equation 16. Another thing that can happen is that you can also say that you can do many things with the equations. All right. So that's that about electric potential. Now, quickly, let's move to capacitors. Now, let's quickly talk about capacitors and capacitance. Now, a capacitor is a device that is used to store electric charge. Electrophorus is also used to store electric charge. Used to store electric charge. Okay, used to store electric charge. Now, for this capacitor, the measure of how much it can store electric charge is called capacitance. Is the measure of how much it can store electric charge. So we say capacitance is the capacity of the capacitor. I used to like this definition. Do you know why? I don't like it. It's the capacity of the capacitor to store electric charge. Is that okay? Electric charge. So now, actually, a capacitor is composed of two parallel plates, okay? I'm drawing it out because there's a property that I want you to see in its shape, okay? The shape also impacts something, has an influence on the way it behaves. So a battery will be connected here. So this battery is going to run through. This will be the positive plate, this will be a negative plate. So as electric charges is running through it, it's going to be storing electric charge. So notice it has area. So the capacitance, it has a flat surface, right? So the capacitance is actually directly proportional to the area of this disc, of this plate. The capacitance is inversely proportional to the distance between these plates. So that is inversely proportional to the distance. So that the higher the area, the higher the number of the amount of charge to store. And the lower the area, the lower the charge. The higher the distance, the lower the charge. The lower the distance, the higher the charge it will store. Is that clear? So by the time we bring this together mathematically, it becomes C equal to epsilon naught A over D. So this is the equation that connects them, capacitance. And there's something you must also know about capacitance. I said that capacitance is the quantity of charge stored per voltage that is run through it, right? So that's Q, so this will become equation 17, and this will become equation 18. So by the time you do this, you know that Q is actually equal to CV also, and this is equation 19. There's something called, now there's something we also calculate, is the energy stored. The energy stored, I would have derived this for you too, in a capacitor, but just remember that it is equal to half CV squared. Now let's start with half QV. So if it is half QV, Q is CV, or by the time you put CV here, it becomes half CV squared. V from here will be equal to Q over C, right? So by the time you put Q over C here, it will become Q squared over C. So, or half Q squared over C. So that will be Q squared over 2C. So these are the formulas you need to know to solve questions on that capacitor. The other thing you should also know is the arrangement of several capacitors. What if we put capacitors together like this? This is the circuit notation for it, the circuit, we will represent it in circuit diagram. So this capacitor will have capacitance 1, here this one capacitance 2, capacitance 3, capacitance 4, capacitance 5. By the way, capacitance is measured in farad, okay, measured in farad, short for Faraday, okay. So now I now said there's capacitance arranged in series. This arrangement is called what? Serial arrangement. So this is in series. When you have this, the total capacitance or equivalent capacitance, means this thing you arrange in series is the same as connecting the capacitance of 1 over C1 plus 1 over, to be 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over any amount of CC up to CM. Is that okay? But we arrange them in parallel. I'll solve question on this. Maybe so that I will show you how to resolve circuit. If you arrange them in parallel, then that is, you arrange them like this. One like this, another one, we have them like this, like this, like this. Keep in mind that this one is voltage for battery. So this one is parallel plates. We call them parallel plate capacitors. That's why you see the plates are alike. So if we call this one C1, C2, C3, C4. Now, in your textbook, you might think that they always have to be upon each other. It's correct, okay? But this thing is the same. It's still parallel. This is still parallel. In as much as they are separated by junctions, okay? Once you have this arrangement, the equivalent capacitance is equal to C1 plus C2 plus C3. Don't confuse it with resistance. With resistance, if you arrange resistance in parallel, to be 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. But if you arrange resistance in series, R will be equal to R1 plus R2 plus R3, blah, 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 to Rn. Is that clear? So that's one part that usually confuses students. Let me quickly solve like 1 or 2 questions on that. How do we resolve a circuit that looks like this? The circuit says find the capacitance, or maybe the energy stored. I don't know. or the quantity of charge stored when the capacitance, when in this circuit, for example, we have a circuit that looks like this. Let's say 6 volts is connected, and we have 3 mil-farad here. Here we have 2 mil-farad. Here we have 2 mil-farad. Here we have 4 mil-farad. Mil-farad means microfarad. So how do we resolve something like this? It's very easy. Now these two here, are they in series or parallel? They are in parallel, right? On top of each other like this. They are separated by junctions, right? Now for A-level students, I'm going to deal with junctions, nodes, mesh, all right? And loop. Now you see this guy, we'll now find the equivalent capacitance here. That is that they are like this. C will be equal to what? C1 plus C2. Okay? So C will be equal to what? 4 plus 2. That becomes 6 mil-farad. I'm able to add them directly because they have the same quantity. Mil. Mil, by the way, means times 10 to the power minus 6. So just check out my video, you're going to see that. So this 6 mil-farad is the same as, these two connections you are doing is the same as just putting a 6 mil-farad in this one. By the time you do that, you now do, so your circuit, after getting this answer, has simplified to what looks like this. See, this circuit has become this, where this one is now 6 mil-farad. So in this case, you can now do all of these guys in what? Series. They are in series. So it become 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. So that becomes 1 over C equal to 1 over 6 plus 1 over 2 plus 1 over 3. Fortunately, the LCM is still 6. 6 in 6, 1 times 1 plus 2 in 6, 3. 3 times 1, 3 plus 3 in this 2, 2 times 1, 2. So 1 over C becomes 1 plus C, 2 plus 3, that's 6. 6 over 6, that's 1. So 1 over C equal to 1. Therefore, C equal to what? 1 mil-farad. What we now say is find the quantity of charge stored. Quantity of charge is equal to what? CV, right? So you just say, what's the V that is given? 6. 6 times, what's this guy? 1 mil-farad. Sorry, let me clean this place well. I didn't bring that. So 1 mil-farad. So Q therefore stored by this charge stored by these capacitors altogether will be equal to C, which is 1 times 10 to the power minus 6 mil-farad. Then times V, which is 6 volts of the battery. 6 times this becomes 6 times 10 to the power minus 6. Quantity of electricity is what? Will be in coulomb. So this is what? 6 mil-coulomb. Micro-coulomb. Is that clear? So that will be it for revision on electrostatics. I hope I'll be able to do justice to it. Do have to subscribe to the channel and look out for my video on O-level electrodynamics. We're going to deal with current electricity. God bless you as you subscribe to the channel and share the video with your friends. And you also buy the textbook I recommended for you. God bless you.